All right, I am back for the fourth time. I stopped at properties of integrals. One other property I wanted to mention: if you've got an even function, such that f of negative x is equal to f of x, definition of an even function. Then, and let's say for example, I pick any even function will do. So, pick cosine of x. It'll go something like that. And let's say I wanted to find the integral from negative pi over 2 to pi over 2 again. So integral negative pi over 2 to pi over 2. This integral, of cosine of x, dx. And I'm going to talk about why we put the dx next. This area from 0 to pi over 2 is exactly equal to this area from negative pi over 2 to 0. So this integral is precisely equal to 2 times the integral from 0 to pi over 2 of the cosine of x dx. So in other words, when you have an even function with symmetric bounds, and by symmetric bounds I mean going from like negative a to a, in other words, one bound is just one bound of integration is just the negative of the other, of an even function, I'll call even of x dx. That's just 2 times the integral from 0 to a of even of x dx. So why do we add the dx? Well, there's a couple of ways to think about this. One way is that this function here, you could, the first and most basic way is the dx tells you with respect to what variable you're integrating. For example, if I had just integral of tangent of theta dx, that would just be x times the tangent of theta, because plus your constant c, because dx here is telling you with respect to the variable you anti-differentiate. Theta then is just being held as a constant. So if theta is a constant, then the tangent of theta is a constant, and the integral of a constant times with respect to that variable is just that constant times the variable with respect to which you were integrating. So that's one way of interpreting what this dx. It tells you with respect to what variable you're integrating. Now, the more sophisticated approach of interpreting dx is that if I have an integral of a function, most functions have an antiderivative. There are very few that don't. Some ones that you might want to be familiar with, though, are the sine of x over x, cosine of x over x, e to the negative x squared, the square root of x cubed plus 1. And there's some others, but those are the most known ones. But almost every function has an antiderivative. So we could think of integrating f prime of x. Now, there is a dx that goes here, but think about it like this. It really just goes back to the definition of dy and dx, and I don't think Mr. Mack has ever talked about this, so I think I really should talk about it. So, say I have a function, and we're considering from here to say here, let this distance be delta x, and from here to like this point here, let this distance be delta y. And let's consider a point here and its tangent line here, then the distance from where this tangent line meets this line, in other words, from here to here, this is dy. And the distance that you have to travel from where you're starting, namely here, to the x point at where your tangent line is called dx. So dx is this distance here, right here. So in our particular case, delta x is equal to dx. And dy is this distance from where the tangent line to that point of that curve intersects this line, from this point down to where this line intersects that line. That is dy. Now notice, as delta x gets smaller and smaller, in other words, as delta x goes to 0, delta y approaches dy. If this function were, we have, right now we have y is equal to f of x. If we had if we had instead x being equal to f of y, then it would just be flipped. Delta y, as delta y would go to 0, where delta y would be the same as dy, then delta x would approach dx. So the difference is that dx is the differential of x. This differential measures this distance here, because remember, the tangent line was built on an approximation. And that approximation was that the two secant lines are going to come together. Now, they can't actually come together, so we take their limit. Now, so they're going to be off by a little bit, and that little bit is dx. That little bit is dx. So what this dx here tells us